it is impossible, like Shadman Bhai said, to complete a GR course in 2 lectures. So of course, I'm going to breeze over a lot of topics, but first I would like to mention that I do have my lecture notes ready. So if you want to have them, maybe we can give them to the give the lecture notes to the audience so that you can follow the lecture. And so another note that I want to make, since we have very limited time, I would appreciate it if you could ask the questions at the end of the lecture. Okay, so even if you have a question in the middle, note it down and asking at the end, I will answer. Arekta note hoche je I would probably mix languages because I think it's easier to explain stuff intuitively when I'm speaking when I'm speaking in both languages. So I mean probably Bangla bolbo, English bolbo, and I will probably mix my languages. So sorry for that. Okay, so let's start with the lectures. So since I'm giving a lecture on 2 lectures on general relativity, we might first start with the question of why we need a general theory of relativity. In fact, we understand that general relativity is a gravity theory, and we already had a gravity theory to begin with, right? Because Newton worked with gravity, he postulated a gravity theory that worked perfectly fine. We could predict sort of celestial orbits and all of that stuff with, local gravity theories like Newtonian dynamics. So the question remains that why do we essentially need a general theory of relativity? Why did we have to modify it? So the first thing to note is that we require a general theory of relativity because it does not predict high gravitational fields very well. So, for example, have you ever seen Newtonian mechanics explain the area around black holes? No, right? So the area around black holes is an area of very high gravitational fields. So Newtonian mechanics cannot explain that. And therefore, we need general theory of relativity, something that relates, well, spoiler alert, geometry to define something of high gravitational fields. Right? So that's one point to why we need GR. So to explain high gravitational fields. The second point to why we need general theory of relativity is because we don't have an idea of the speed of gravity in Newtonian mechanics, right? Because in Newtonian mechanics, or in fact Newtonian force, the gravitational force, it's essentially irrespective of distances, in the sense that, well, not exactly distances, but in the sense that it does not travel, right? Because it's an instantaneous force. Gravity just works. But how does it work? It does not explain, but we don't explain it through Newtonian mechanics. However, as we know from general relativity, gravity travels, right, through gravitational waves. In fact, if the sun were supposed to, let's say, disappear now, we would not feel its effect, the disappearance, until 8 minutes from now. So therefore, we know that gravity does not work instantaneously. Gravity travels, and therefore there is a speed of gravity, and that is traversed through gravitational waves, which is beautifully explained by general theory of relativity. Another thing to note to why we need GR is the fact that we have time warping, right? Newtonian mechanics does not explain time dilation very well. But we know that if you're traveling around a strong gravitational force, gravitational field, time acts differently for us with respect to other observers that are not in a high gravitational field. You've all watched the movie Interstellar, right? And we know that if we're around a black hole, time moves slower for us than for someone who is not in a high gravitational field. So therefore, Newtonian mechanics does not explain this time warping or time dilation. GR does. Right? So therefore, we need this particular theory that explains all of these attributes of gravity, and therefore we work with GR. And GR is essential because GR is one of the fundamental sciences or one of the fundamental theories that can explain grand scales. So if indeed we are to explain the universe, if we want to understand what happens at these grand scales, we need a basic framework like GR to explain our theory. So that's why we work with GR. And now let's work with it. So let's start with something very basic, which is the equivalence principle. So it's called general theory of relativity, right? Why is this general? And why do we have a special theory of relativity? So of course there are many reasons to this, but to cut it short, basically there is a relationship between GR and SR through the equivalence principle. So if I am to explain it in like a short statement, what the equivalence principle basically states is that locally, even if we are working in a curved space, locally you can modify it as a flat space and imply SR to it. So therefore, GR can be locally treated as SR. Okay. So basically, if you have a curved manifold, a curved space, you can locally treat it as a flat space and work with the physics of special relativity. So that's what the equivalence principle is. And furthermore, equivalence principle has another statement. Let me write that down for your reference. Which essentially states that there is no observable distinction between the effects of gravity and acceleration. So this statement basically means that if you have a gravitational field, there is no observational difference between that of the gravitational effect and if you were working in a non-inertial frame of SR. Okay, so in a non-inertial frame is where we introduce acceleration in special relativity, right? So therefore, there is no difference between the two, and in fact, for this particular reason, you can relate GR and SR. Okay, so one of the most fundamental consequences of the equivalence principle is gravitational redshift and time dilation, and you will see in a bit that we can actually relate the two. So let's first talk about gravitational redshift. So we all understand what redshift is, right? Basically Doppler effect. We understand what Doppler effect is. It's essentially when you have a moving observer and you're observing that moving observer, either you're stationary or you're moving as well, you will feel that the transmission or any sort of light waves that that particular moving observer is emitting towards you will be shifted in wavelength. Okay, so if I have a red shift, it means that the wavelength will be shifted towards the red spectrum. Okay, that means it's stretched. If I have a blue shift, then the shifted wavelength will shift towards the blue spectrum, which means it will be contracted. So that is basic Doppler effect. So around the gravitational field, we will have gravitational redshift. Basically, the transmission from an observer, which is, let's say, stationary or moving in a gravitational field, we will see that that transmission is redshifted. So let's look at that from an examples perspective. Let's take two observers, which they are in uniform gravitational field. So let me draw this so that you can relate to it. Let's say I have two observers. Let's call them with generic names Alice and Bob. Okay. And let's say Alice transmits some wave or light to Bob, and Bob receives it. Okay. And let's give them some coordinates. So let's say they are on the z-axis, and gravity is working downwards. So we have G downwards. Okay. Now, if we take Alice and Bob to be moving, then let me sort of conjure their coordinate points. Let's say this exists at some ZA, and this exists at some ZB, okay, on the z-axis. And of course, Alice will send out the signal, and that signal will have a particular wavelength. And let's say that wavelength is equal to lambda A. And the wavelength received by Bob, let's denote that as lambda B. Okay. Now, if we take Alice and Bob to be moving with an acceleration g, which is given over here, we consider this particularly in Minkowski space, which is a flat space, because we can, like I said, imply the equivalence principle over here, right? So even if they are in a gravitational field, even if they are in a curved space, locally we can consider them to be on flat grounds. Okay, so let's consider them to be in Minkowski space. which is flat. Okay. Now, we are assuming, of course, that del V by C is very small because we're working in SR. One of the postulates of SR is that C is the limit, right? So therefore, any sort of change in velocity would be much less than the speed of light. So therefore, we consider that this is very small. And V is essentially the speed of the wavelengths as they travel, okay? The speed of the signal. So light will reach Bob from Alice after some time t. So light reaches, let's say, at some del t, which we can write as some h of c, where h is the distance between Alice and Bob. Okay. And Bob's velocity, as both of them are moving, I can write this as some del v equals to g. So now from here, and because we will have some sort of Doppler effect, because both of them are moving, I can write the Doppler effect equation in the following way. And this will equal to. Now, by the equivalence principle, this particular wavelength, which is starting from Alice, let's call that lambda naught, because I want this to be the initial wavelength that Alice transmits, right? This particular lambda naught will be redshifted, right? And using the Doppler effect equation, I can write this in the following way, where I'm saying that this particular expression, or delta phi, is equal to GH, essentially the difference between the gravitational potential, okay? Because the gravitational potential will be a factor of the height. So in this particular aspect, we can also think the gravitational redshift as a time dilation. Why is that? Let's look at this. So if I consider the period of the emitted light, let's call that TA, because the emitted light is coming from Alice, that's why the subscript A. This would be given by lambda A by C, right? In the period, time. So this would be some wavelength by some speed, right? And I can imply this and also find a similar relationship for the period of the light that Bob receives as lambda B by C. Okay, and I can relate the two by incorporating the period equations in the Doppler effect equation, and I will have TV to be 1 plus phi b minus phi a divided by squared. Okay. Now, since Alice is existing over here and Bob is existing over here, which person do you think will have a higher gravitational potential? Bob, right? Because Bob is higher than Alice, so obviously Bob will have a higher gravitational potential. So we can write phi b to be, sorry, greater than phi a. Also, similarly, if that is the case, if we incorporate this over here, if indeed phi b is greater than phi a, then TA should be greater than TB, right? So if that is the case, then, oh, maybe I wrote this wrong. TB should be greater than TA. You understand why that happens? Because if phi b is greater, then this would add to TB, right? Because then therefore TB would be greater than TA. And in that case, I can say that the time that Bob feels is much greater than the time that Alice feels. So that means the clock for Alice runs slower than So if that is the case, then I can write, if indeed this is the case, I can write the time runs slower for Alice than for Bob. And if that is the case, that means a clock in a gravitational field will be slower than a clock that is not in a gravitational field. So therefore, there is some sort of gravitational time dilation that is happening over here. Okay, so that means gravity slows down time. And in fact, it doesn't only work for clocks, it can work for any sort of ticking devices like clocks, even for heartbeats. Okay, so if you are in a gravitational field with a heartbeat, then your heart will beat slower than that of a person who is not in a gravitational field. That, which means essentially you will age slower. And if you're around a black hole, you might be young forever. So moving on to another concept in general relativity. So we understand that in GR, but we basically say that gravity corresponds to curved space. Right? This is something that we've all heard. Even if you didn't do GR, we've always heard this about Einstein's theory of relativity, right? That we have a certain fabric of space-time, and then if you put an object there, it will curve space-time and so on. So putting an object over there is basically introducing gravity, right? So if you introduce gravity, that curves space-time. But why do we think it's so? So why do we actually correspond gravity to mean a curvature in space-time? So let's look at that. So let's look at this example again, but instead of just one light signal transmitting, let's consider two pulses of light. Okay, so I'm saying that Alice at some ZA where she exists, and I'm assuming Alice is a girl, is transmitting a light to Bob. Okay. And then after some time, she transmits another light to Bob. Okay, so the time difference or interval between the two pulses, let's call them delta A, and let's call this delta V, the amount of time interval that Bob feels while receiving the two pulses. Okay, so essentially, we would think that this interval delta A and delta V would be the same, right? I would think that this is true. That exactly the amount of time after that Alice sends the light signal will be the exactly amount of time after that Bob receives the signal. But if that is true, then this basically contradicts the statement over here, right? This contradicts the fact that we have a time dilation. And time dilation এই যে ইকুয়েশনটা সেই ইকুয়েশনটা কিন্তু আমরা হচ্ছে essentially we derived it from known stuff like Doppler effect, which is an established truth. We do have Doppler effect, right? So this cannot be false. So that means this has to be false, right? So what is the answer to this paradox? In fact, is the interval of pulses not equal? And if it is equal, how? Because it contradicts. There is a certain paradox to this, right? So the answer to this is that while we computed this, we considered that this is happening in flat space, right? Because এখানে কিন্তু আমি assert করে দিছিলাম that this is in Minkowski. So therefore, if we assume that this is in flat space, we have a paradox. And hence we must extend our thinking to think that perhaps space-time is not flat. Perhaps if we have a gravitational redshift as such, it must mean that we have a curved space-time. And that's why gravity or gravitational fields, if exists, should equal to curved space-time. Now let's try that out. Let's consider a very weak field, a weak gravitational field, and write a line element in that particular gravitational field, d squared. So d squared is just a distance in a space from one point to the other. Okay, so if you have point A, point B, and the distance that connects point A and point B is given by d squared. So let's look at this explicitly. So আমরা যদি Minkowski space এ কাজ করি, normally আমরা Minkowski space এর line element likhi as the following. Okay, so I'm writing a bar on top of 3 vectors, okay, just for your reference. But we want to discard this, and we want to initiate a certain weak field. And in that case, let's take the line element to be as such. Okay, and then let's consider this line element and do our computations. So here I'm considering that phi is much, much less than c squared because this is small. Okay, so this is essentially a weak limit constraint we're putting over here. So in these coordinates, Alice sends a signal at TA and another one at TA plus some del t. Okay, and Bob receives the signal at TB and another one at TB plus del t. So this essentially should be the same because time for their respective clocks are the same, right? Interval. So in this case, I can write these del t's with respect to their proper times because proper time is, let's say, established, right? Because আমি যে টাইমটা ফিল করব is stationary for me, constant for me. So if I walk around here for 2 minutes, I will be walking around here for 2 minutes, whether I'm in a gravitational field or not. So my proper time, the clock that I count, is constant. So therefore, it will be easier if I define these equations with respect to proper times. So in that case, let me write the proper time with the tau of Alice, and this will take. So you can tell me how I would define it, right? So the proper time would obviously be dependent on your line element over here, specifically the time component of the line element, which let me call this as okay. Now, if you're familiar with what G is, good. But if you're not, let's just keep it as is. Okay, G00 is basically just the first component of the line element, which is this one over here. Okay, so let me replace that. And I can write this as 1 plus 2 phi c squared. And the minus is just for convenience because we have a minus signature over here. Okay. So in this case, I can write this to be approximately, if I expand this for small phi, I can write this as approximately phi a by c squared del t. Okay. And the same computation I can do for delta tau b, which is the proper time for Bob. And I can write this as approximately. Okay. If I want to relate the two, combining the two equations over here, you will see that delta tau b will be something like 1 plus phi b by c squared. It is 1 plus phi a by c squared inverse delta tau a. And I can approximate this to be 1 plus phi b minus phi a c squared, which is exactly same to the time dilation equation that I had above. This one, right? So that means what? By initializing a gravitational field, you get time dilation. And therefore, this must mean that once we have a gravitational field, we are working in a curved space. And therefore, gravity corresponds to curved space. Okay. Now, since we are here, let's talk about the metric. Okay. So, like I said, the line element essentially describes a distance between 2 points, right? You have some space, you have 2 points, again, point A, point B. The distance between point A and point B is defined by the line element, ds squared. Okay, so ds squared is normally defined by the metric. And in physics, we write this to be the following. Okay, so what is happening over here? Let's try to think. So I have some ds squared, which is supposed to be a distance squared. right? I also have some distance stuff over here, which is also producted. So this should give you some square of some distance, right? Then what is this one? So I have distance squared on one side, I have another distance squared on another side. What is this particular thing in the middle? What does this imply? Okay, so this is the metric. Okay, so let's try to think about this intuitively. What is this trying to do? If ds squared in fact defines some sort of distance between 2 points, then how I go from point A to point B should be determined somehow. For example, take this board, right? If I'm walking from here to the computer over there, I'm traversing some distance, right? And it depends on how this floor is shaped in the way I traverse to this point to that point, right? So let's say if this is a straight line, I just walk in a straight line and I will reach that computer over there. But what if this is not straight? What if this is a sphere and I'm walking on a sphere from this point to that point? Will my distance then be the same? No, right? আমি যখন এখান থেকে ওখানে হাঁটতেছি in a flat space, I can just draw a straight line from here. But if I'm walking on a sphere, I cannot then draw a straight line. তখন হচ্ছে distance will not be a straight line, but it will be some sort of line depending on the geometry that I'm working on or walking on, right? So that particular difference in the distance is given by this metric. So that means the metric must define a certain idea of geometry that I'm walking on. So normally I'm in the flat space work, but let me say I'm walking from this place to that place in the flat space, then G mu should be flat. It should just give me an equation of a straight line, right? But if I'm not working on flat space, if I'm working on a sphere or a curved manifold or space, in that case, G mu should give me exactly that amount of contribution that deviates my distance from flat space. Does that make sense? So therefore, G mu will give me an idea of geometry, and that is what we call the metric. Now, the way I define the metric again, let me just go to basics, is through this distance parameter, where I'm saying that, let's say I have 2 points existing at P and another existing at Q. Okay, and the difference between P and Q is given by D, and I can write D as the following. Okay, so you see that I have an integral that basically should give me a distance between the two, and I have two inner products of tangent vectors, right? So these are tangent vectors over here. Okay, let me write that down for your reference. So I know maybe I'm not defining everything properly, but it's just because of limitation of time. Okay, but my notes are more, they're better. Okay? So just trust me. So I can define this as the distance, and you see that I have an inner product of two tangent vectors. Right? I have an inner product over here. So depending on the distance that I'm computing over here, let's say it's on a curved manifold, this particular inner product has to be generalized because a distance is being defined by this inner product, right? So let's generalize that particular inner product. So an inner product maps a pair of vectors to a number. And at a particular point, let's say at a point P, we can write this map. Let's denote the map as G. So if you don't understand this, just think of this as taking two tangent vectors and the product is giving me a real number. So you're taking a vector and the inner product of these two vectors are giving you a number. Okay. So to make this a 0-2 tensor, and why I'm saying that this has to be 0-2 is because you see that I have two indices here, right? So this has to be a 0-2 tensor. A 0-2 tensor essentially just means that you have two covariant indices, as in downstairs indices. Okay, so in that case, I need to abide by some following conditions: that G must be symmetric, which means that if I take two objects and map them, it should be the same as just shifting their order. Okay, and another note is that it has to be non-degenerate, which basically means that determinant of G mu is not equal to 0, and therefore the inverse of G mu exists. Okay. So in the coordinate basis, normally we write G as G mu nu dx mu tensor product dx mu. Okay, so this is a tensor notation, and these are components. Okay, so in a coordinate basis, we can write it like this. So what mu and nu are, they're indices that tell you how many dimensions you have in the coordinate. So let's say if I'm working in real space-time, I would have 3 spatial indices and 1 temporal index. Okay. So over here, this equation actually resembles ds squared equals to g mu dx mu dx mu, right? But I'm not saying that they are the same. So I'm denoting one as g and the other as ds squared. Where is the difference? Now, the way I wrote this is in my notes. I can't write like typeset my handwriting, but in the notes you will see that the way I write this is in the following way. Okay. Now these are actually one forms. But on the other hand, these are little, let's say, curly are differentials. Okay, so what differentials mean are basically taking an infinitesimal limit to delta x. So if you take it infinitesimally for infinitesimal x, you would get a differential, right? But one forms are different. One forms are not infinitesimal limits. So we can define these two and relate them if we are acting a one form on a vector. Let's say we're computing the one form on a vector, and let's define that vector as where this is the differential. Okay, so just follow my notes if you're confused about my writing notation. So if we are acting the one form on the vector x, then we would get the one form. Let me just write the one forms with the bar so that you can understand the differential mu. So this is coming from the definition of the vector. And I can write this as mu dx mu del mu. And these two should essentially give me a Kronecker delta because I'm working this differential on the partial derivative, and they will be equal only if mu and nu are equal. At least, as in they should give me one if when mu and nu are equal. And therefore, considering this is true, we should get. Okay. So in this case, you can relate the one forms and get a differential. So let's do that. What we're going to do is now we're going to act the one forms on the vectors. And I can write this as, this should be ds squared. Okay, basically what's happening is that the one forms are acting on the vectors and you're getting the two differentials out, which is equal to d squared. Okay. Okay, so now from here, since we have two properties of the metric, let's work with the first one. The first one basically establishes symmetry. So that means that I can write the components g mu nu equals to g nu mu, as in I can shift the order and they would still be symmetric and therefore equal to each other. That basically means that we can always find a basis for the metric tensor where it diagonalizes the matrix, the metric matrix, okay? Which just basically means that we will always have a metric matrix with just diagonal components, okay? Now, property 2, which is the non-degeneracy condition, means that we will always find an inverse for the metric component. So therefore, it means the determinant of G mu is not equal to 0. And we can write, therefore, an inverse for this. Let me write it in notation, which would give me some Kronecker delta, right? So in GR, we don't basically work with indices that look the same because it can be confusing. So let me denote this differently. So let me write this. Let me write the inverse as indices at the top. Now, if you've done differential geometry, you know where this comes from, right? This is a basically this is a contravariant component of the metric, while we call the downstairs indices as covariant components of the metric. Okay, so contravariant components and covariant components are inverses of each other. So in this case, if I have an inverse of a covariant component, it will give me the contravariant component of that particular metric, right? So if I invert G mu nu downstairs, I should get G mu nu upstairs. So I can write this as the following. And if they are indeed inverses of each other, it should give me a Kronecker delta only if mu is equal to 6. Okay? Because basically, if you make a product of inverses, they should give you 1. Only if they're inverses of each other. And this is true if the indices are the same, if mu equals to sigma. Okay. So now let me just jot down some points. That is, the number of positive and negative eigenvalues of the metric is independent of the choice of basis, and it's called the signature. Okay, so the number of positive and negative entries is called the signature. Okay. And normally, if all eigenvalues or of all the diagonal entries are positive, we call it a Riemannian metric. Now, you may ask that if this is true, what kind of metric are we in? Us. Reality. What kind of metric can we use to define reality? So from our examples over here, you saw that I did write a metric, right? Over here. Because ds squared is given over here. And essentially, I can write these as something like this. So that would mean I have coordinates over here and something in the front. So the coordinates are given by t and x because I have 3 spatial coordinates and 1 temporal one. So t and x are basically those coordinates. Then therefore the signs should determine the metric, right? But over here I have a negative entry of the metric. And that would mean that the eigenvalues, or basically the diagonal entries that I'm considering over here, can be negative in reality, right? So that means that we are not working in a Riemannian metric. We do not exist in a Riemannian metric, but we exist in a pseudo Riemannian metric. So life exists in a pseudo Riemannian metric. So pseudo mane hocche essentially Riemannian, but not really. Okay, so we have all of the positive entries, but we have one negative one. Now you can choose your signature. You can choose to have the temporal component to be negative and the spatial to be positive, or you can choose the temporal one to be positive, all the spatial ones to be negative. It's your choice. Okay, so if you use the temporal one to be negative, we call this mostly plus signature because you have the other three to be positive. And if you choose the other way around, we call it mostly negative. Okay, it's just the way you do things. Now, if we're done with that, we need to, yeah. I'm not doing a tensor product between the two differentials. AJ, because they are related, they are not the same, right? One forms are not differentials, essentially. That's why I said, look at my notes. My notes has it, like, I cannot write it over here properly. I'll write the same D. So this is the differential, okay? The one that is with the tensor notation. Because you have a tensor product. But the ones without is the differential. Okay, so just take a look at my notes. That's why I gave the notes out, because I knew I was not going to be able to write this. But for reference, just please follow it. And I niche, I think I gave a bar to the one that is a one form. Yeah, this one. Okay. Can you see my pointer? But I can't see my pointer myself. Anyway, so moving on. So we have all of this done, but the question is, why? What do we do in general relativity essentially? Okay, so GR basically has two key points. একটা হচ্ছে one idea that we understand space-time curvature tells us how to move. Like I said, if this particular space was curved, how I go from this point to that point would be determined by the curvedness, right? So therefore, space-time tells us how to move. আরেকটা point হচ্ছে যে matter tells space-time how to curve. Because like I said, gravity is corresponding to curvature. So therefore, if I have matter, I have gravity. If I have gravity, I have curvature. So therefore, GR এর দুইটা key idea আমরা এখানে বলতে পারি essentially যে space-time tells us how to move and matter tells space-time how to curve. So এই দুইটা জিনিসকে আমি যদি লিখি, tells us how to move. That means that আমাদের কোনো ধরনের একটা dynamic equation লাগবে, right? Essentially যে move করার বিষয়টা যেহেতু আসছে, therefore we need an equation of motion, right? Something that determines how we're going to move from one point to the other. So this will be followed from the equivalence principle. And the other point that matter tells space-time how to curve will be given by the famous Einstein equations. So this is basically GR's two key ideas, and we will follow up on these two ideas. So since we need to have a certain equation of motion, we definitely start with the action, okay? And the basic action is of an action of a point particle. So let's start with it. So if I want to write the action of a relativistic point particle, and in natural units, meaning c equals to 1, I can write the action as the following, okay? Now, from here, I know that if I take a variation of the action and equate it to 0, I should get my equations of motion. Like this is something that we saw even last class during QFD lectures, right? If you take a variation of the action and the path that extremizes the action, meaning the variation goes to 0, is the path that a particular particle follows, right? So therefore, by extremizing it, taking the variation equal to 0, this should give us the equation of motion of that particular point particle. So let's consider again the 2 points P and Q. And I can have many ways to go from P to Q, right? But the particle will only choose the path that extremizes the action. Okay, and this path is called the geodesic. So therefore, this geodesic equation should give you the equation of motion of a particle once it travels from P to Q, or from any arbitrary point A to B. So therefore, this is our equation of motion in a generalized setting. It can be flat, it can be curved, we don't know. We just want to generalize it. So now let's move to this geodesic equation. And we want to study the motion of particles in a general space-time, as in non-trivial space-time. It's not just flat space. But if we do consider flat space, then এটা generic না যে the geodesic equation should just give me the equation of motion of a straight line. Because if I am on flat space, the least action principle, or del S equals to 0, is a straight line, right? From one point to the other, the one that minimizes the action should be a straight line. So therefore, geodesic equation for flat space or generic Minkowski space just gives me the equation of motion that we've studied in classical mechanics, right? However, for non-trivial spacetimes, if we have curvature, the geodesic equation should essentially give you something that contributes from the geometry of the space. Right? So let's try to build that. So, like I said, a geodesic is the preferred curve for which the action is an extremum. And the curve that satisfies the geodesic equation, which I will just write over here and build upon it later, is the following. Okay, where we have introduced the Christoffel symbol as, this is a definition. Okay, now over here, this may look like a tensor, but it's not. Okay, it's just a number. It's just a component which gives you a number essentially. So this is not a tensor. Okay. Now, using this, আমি তো জাস্ট জিওডেসিক ইকুয়েশনটা দিয়ে দিছি, বাট এটা কোথা থেকে আসছে ওটা তো বুঝতে হবে আগে, right? So first of all, let's try to prove this. I don't know if I have the time, but let's try to prove this. So the action in general, like I said, I can write it as the following with time, right? D tau over here, like I wrote, and D tau you can write it using the metric, right? And if you remember, this is something that I did earlier as well. So আমি এখানে এখন পুরো মেট্রিকটা নিই, mu. And let me just call this whole thing to be G. I think that will be easier for us to complete. Okay. So finding the path of extremal action is basically then just doing calculus of variations, right? You vary the action and equate it to 0 and so on. And from classical mechanics, we know by variation principle you get the Euler-Lagrange equation, and this is something that we've touched upon yesterday as well. So তার মানে হচ্ছে, if you have a geodesic equation, basically the path that extremizes the action, you should have it satisfy the Euler-Lagrange equations, right? So the Euler-Lagrange equations is given by the following. So let me write for a general case. And for our case, since we are denoting this as G, we should get something like, to be a total derivative. Okay, so therefore the equation that satisfies This particular relationship should be our equation of motion, therefore should give us the geodesic equation. So I'm going to skip a lot of the derivation over here, but it's on my notes. So if you have to catch up on it, you can come to me later on. But from here, let me just write the end expression, which is given by okay, and this should equal to 0 because again we're extremizing the action, right? So from here, if I contract this whole expression, or basically multiply this whole expression, so let me just call this contract by an inverse metric, what I will get is, so let's see what happens essentially. So I'm using G sigma mu, which is upstairs, they multiply Kureta over here, then this should multiply with the G mu nu over here, right? So the G mu nu over here should be multiplied with the G sigma mu over here, right? And since they are upstairs and downstairs, we should have a delta, right? And that delta should potentially change mu from here, right? Because our kind of mu is the same, mu is common. The only thing that is not common is nu and sigma. So therefore the Kronecker delta should be on nu and sigma, and therefore it should convert nu to sigma. So therefore what I will get is the nu from here to be equal to sigma. So therefore I will get t squared sigma by, okay, on the first term. And the rest I can just keep as is, except with an inclusion of the term that I'm multiplying, and the rest will follow. This equals to 0. So agent purata part from here is my Christopher, which I write as the following. So let me just keep writing and just denote this as the Christopher. This whole thing. Okay. Now I can relabel the indices and I can write this nicely in a more concise fashion. And I can write my geodesic to be the following, and this gives you the geodesic equation. So geodesic equation is essentially action principle থেকে আসছে, which is an established fact. This is how we find equations of motion. Therefore, this must be the equation of motion for non-trivial spaces. That means now you have a crystal over here, which is defined by the derivatives of the metric. So metric এর কাছ থেকে আমি geometry আইডিয়াটা পাচ্ছি, right? Because like I said, metric gives you an idea of the geometry. So metric থেকে আমি geometry আইডিয়াটা পাচ্ছি, and I'm adding this to the equation of motion. So আমার যদি মেট্রিকটা ফ্ল্যাট হইতো, okay, তখন আমার geodesic equation should just boil down to this term, which is the equation motion for straight line. That is something that we know from classical mechanics. তার মানে if I don't have curvature, your crucible symbols go to 0. Okay, and since the crucible goes to 0, that means crucible symbol থেকে আমরা একটা geometric idea পাচ্ছি, and this particular term is essentially what deviates the equation of motion from straight line. So straight line হলে তো আমার d just second derivative term equals to 0 হতো, but now I don't have that. I have another contribution which comes from the contribution of geometry through the crucible symbol. Okay? So this is the geodesic equation, or basically the equation of motion for non-trivial spaces. You can compute it for flat space, you can also compute it for curved space, depending on what type of metric you're working on. Okay. So now, since we're in the topic of curvature, how much time do I have left? 30 minutes. 20 minutes. Okay. Okay. Anyway, so that's good. So since we're in the topic of space-time curvature, let's try to understand what happens when a particle moves in curved space-time. And that is important for us because essentially what we're doing in physics is trying to understand how things move, right? And since we're doing general relativity, we need to understand how things move in a non-trivial space. So আমি তো এখন মুভমেন্টটা ডিফাইন করে ফেলছি জিওডেসিক ইকুয়েশন দিয়ে, বাট আন্ডারলাইং মুভমেন্টটা কিসের কারণে হচ্ছে সেটা আমি এখনো ডিফাইন। So I need to define what space-time curvature is, or basically how we think about space-time curvature in general relativity. So particularly in Euclidean geometry, parallel lines stay parallel, right? Which means that if I have two parallel lines over here and they're traveling, the curves traveling, in that case, they will always travel at a parallel distance if you're in Minkowski space, in flat space, which is basically given by Euclidean geometry. However, when the geometry is curved, in the sense that if we have curved space, they might not stay parallel, right? So in that case, we need to understand what stay and what parallel means in a curved spacetime or in a general geometry sense. So before we can answer these questions, we have to first understand how to take a derivative on a curved manifold. Karon derivative দিয়ে আমরা বুঝি কি? Some change, right? And if the curves in fact evolve while it's traveling, therefore we can understand what type of geometry they're on, right? If they stay constant, then they're parallel, they're moving on flat space. But if they don't stay constant, if they're evolving, then we can have an idea of what type of geometry they're lying on. And another point which is derivatives are of course dorkar, because we need to compute the equations, right? So in that case, we need to first understand how to take a derivative on a curved manifold. So let's first try a derivative, which is something that we know, like a partial derivative. Okay, so let's first show that ordinarily partial derivatives are not actually good enough for us when we're working on a curved manifold. So let's define a particular vector. Let's say I'm taking t mu nu, some vector. So sorry, t mu, some vector. And if I want to take a partial derivative of that, this should give me the partial derivative. And I want to see what happens if I use this partial derivative in a general coordinate transformation. So in that case, if I take a coordinate transformation as such, let me redefine the partial derivative, including this particular coordinate transformation. And after computations, I can use the chain rule over here, right? And after using the chain rule, what I will get, let me just write the result. The derivation is in the notes if you want to look at it. Plus some extra term. Okay. So now, normally when we have a coordinate transformation as such, we expect the tensor to transform like a tensor. Right? That is, I think, the most trivial definition of a tensor, that the tensor transforms like a tensor. So in this case, we would require that, right? But here, if it indeed transformed like a tensor, we would only have this term. But the second term would not be there, right? So why are we having this second term? That means that this particular second term spoils the transformation from it being transformed like a tensor. So in that case, I know that the partial derivative, therefore, is not accurate. We need another definition of the derivative that we can imply on a curved space. So that is why we introduce or define a new derivative, which we're calling the covariant derivative, which is given by this notation. Okay, we're using a nabla. So the way this is defined, let me define it later, but let me first see what happens if we imply this in the coordinate transformation that we used. So if I take the same coordinate transformation, let's take x mu to x mu. Okay. In that case, if I imply this, we will see that the new derivative indeed transforms like a tensor, and we will only get this term. Which is good. Now, I'm going to define Corina what this nabla operator is, right? Let me just, tell you some things about it, and we will see how to derive it later on. And I'm sure you've seen this before, but I'm just keeping it for, surprise. So in general, the covariant derivative what it will do is it will take a rank PQ tensor and transform it to a rank PQ plus 1 tensor. So what are these? So we understand the ranks of tensors, right? P and Q basically initializes your number of indices that you have, let's say, on top and bottom, right? So since I have one bottom over here, right, this basically adds one index to the bottom index over here. So basically, if I have, let's say, T mu, right, I would call this a 1,0 tensor, right? Now, if I have this added to T mu, now I would call it a 1,1 tensor. So basically, what it does is just adds another rank to the bottom index. That's all. Now, there are some properties of the covariant derivative, and we will see that the covariant derivative actually reduces to the partial derivative in flat space, but again, not to spoil it. Now, the conditions are basically the attributes of this covariant derivative satisfies linearity, which is given by, I'm not sure I want to write this whole thing down because you have it with you. So if it's possible, can you open the notes up and just take a look? So let me just write the properties. So it will satisfy linearity, meaning this particular relationship over here. So if you have a covariant derivative on something that is adding, it would basically be the same thing as operating the covariant derivative on them individually and then summing them. Okay. Leibniz basically tells you that if you have the covariant derivative working on the product, then it works as the product rule. Okay, so you work the covariant derivative on one, keep the other constant, plus the other one, and keep the other one constant, and so on, like the way we use differentiation on products. Additivity essentially assigns that if you have, let me write this down because this is important. If you have the covariant derivative represented as such, you can write this in the following way. So you keep the constants up. And fourth is if you operate them on scalars, let's say if I have this on a scalar, I can just write the following. Sorry. And fifth is that if you want to work this covariant derivative on basis vectors, then we can write it in the following way, where this would equal to the Christopher symbols, where I'm saying that this particular thing where I have beta at the bottom is essentially the covariant derivative with respect to the basis vectors. Okay, so now I know this is probably a lot of just stuff that I wrote, but these are just properties that the covariant derivative is abiding by. Okay, similar to what type of properties that the differential operators abide by. So now I have these things listed down. Let's use them. So basically, if you have a derivative that is working with respect to v on a scalar, then it just spits out the scalar out. So let's say if I have some covariant derivative, let me write it as big D with respect to some v, this should give you spit out the v and multiply it with f. Yeah. Hi, it's multiplied with f. Mhm. Mhm. Huh. Oh, okay. So this should be like a partial derivative. Hmm. Yeah, so I can change my notation in this way. Wait. I mean, notation to okay. Yeah. Let me then write it as this is better, right? I think V of F leaky in terms of, yeah, I think that's better. Yeah. Yeah. So this should be V of, sorry, F, partial of V in the direction of F. Acha. Right. Mhm. And it's just, I'm just generalizing it for F, like any F arbitrarily. Okay. Okay. So, yeah. So now let's use these properties to then devise sort of a general idea of the covariant derivative if it's working on a tensor. So let's take the covariant derivative with respect to v on some tensor t, where I'm saying that t is given by t mu, and v is given by v mu. Let's use another index, v mu. Okay. So now I want to initialize this covariant derivative, and therefore I can write the covariant derivative with respect to v on t would therefore be given in the following way if I expand the definition of t. And keeping this aside over here, I can use the properties to now initialize what it should essentially give me as an expression. So now you can look at the notes. I can use property 2, 3, 4, and 5. And what I will finally have is the following expression. So let me write that down. Okay. Now this basically gives you something that looks like the following. which is essentially something we would expect if I would compute a differential on T, right? So that would mean that this component covariant derivative, which is acting on a component of mu, should equal to this whole expression over here, right? And if that is the case, then that must mean that this particular covariant derivative is equal to the partial derivative on the component of T plus some Kronecker delta acting alongside the component of T, such as T alpha, right? So the reason why I have this is because you need them to be contracted essentially. So you have alpha alpha over here, contracted away, mu over here, but mu is contracted over here. So I have mu over here that is left and mu over here, which determines the indices on the other side. So this is the definition of the covariant derivative, which makes sense. Why? Because covariant derivative আমরা কেন initialize করছি, we want it to be for non-trivial spaces, right? So non-trivial spaces মানে হচ্ছে I can work this on curved manifolds as well, curved spaces as well. So in this case, I can do that because I have the introduction of the Christoffel symbol. And the Christoffel symbol essentially gives you an idea of the geometry. So if I am working on a non-trivial space, I can introduce the metric and I can introduce this over here. Okay? And yes, right. Yeah. Yes, this is what I wrote over here. So, yes. So again, this survives, new survives over here, new survives over here. So this is still abides by the indexes. And alpha is contracted, so we don't have alpha on the right hand side. Okay. So like I was saying, if I now work in flat space, in that case, I would have the Christoffel symbols to go to 0. And therefore, this should now reduce to just the partial derivative for flat space. So it makes sense. For flat space, we can take the evolution with regards to a partial derivative, which is fine. But if we introduce a non-trivial spacetime, we need to introduce a contribution from the geometry, and therefore we use the covariant derivative, which now transforms like a tensor. So from flat space to curved space, we change the relationship of the differentials. And indeed, the conservation of energy, which is something that we've learned from the very beginning, in flat space is given by the partial derivative of the energy momentum tensor, right? So the energy momentum tensor is what tells you the bulk of the energy that a particular space contains. And in flat space, if I want to evolve it, and if energy is conserved, then taking the partial derivative would give me a 0. And this is something that we learn in special relativity. But now, since we are transforming from flat space to non-trivial spaces or curved spaces, this should be transformed to this equal to 0. Okay. That tells you two things. একটা হচ্ছে যে trivially, energy is not conserved in a curved manifold, which is interesting because this is something that we've learned from the very beginning, that energy is conserved everywhere. This is like the universal law that we've studied, right, from the childhood. But in general, if we are considering a gravitational field, this is not particularly true, right? Energy is not essentially conserved from a differential. It is covariantly conserved. That means this could be essentially 0, right? But covariantly conserved মানে হচ্ছে both of them have to be 0 to give you this particular thing. And in fact, this is something that we will see in cosmology, that when you're working in a gravitational field, or if you're working in a space-time that is non-trivial, it is not trivial for energy to be conserved. And energy conservation is amounted by something else. Again, let's not spoil it. So this ends my first lecture. If you guys have any questions so far, I'll talk about it, and I'll go to the second lecture. Any questions? Uh, for references, you can look into Hobson's GR, and there's another book by Bauman on general relativity. These two. Any questions from the audience?